welcome to my engineering physics channel. In previous some sessions, we have started unit number 1, fundamental of photonics, part 2, that is optical fiber. Today's session number is 5. In today's session, we have discussed the various types of optical fiber, the difference between step index and graded index, and the derivation based on acceptance angle and the numerical aperture. So let's start the session. So optical fibers are classified on the basis of different parameters. So the first parameter is nothing but the refractive index. So based on refractive index, your step index fiber and the graded index fiber are the two types of optical fiber. Now, second one is based on modes. So based on modes, your optical fiber is divided into two types, that is single mode fiber and the multi-mode fiber. Whereas in single mode fiber, only one mode of propagation is allowed. Whereas in multi-mode optical fiber, there are more than one mode of propagation supported by this optical fiber. Now, on the base of materials, the optical fiber are classified as glass, plastic and the plastic clad silica. So these are the types of optical fiber. Now the first part is nothing but the step index fiber. So this is the fiber which is based on the refractive index of core and cladding. So in step index fiber, what will happen? Its name suggests that the refractive index is changes within a step. That means if here it is your core material, it has the refractive index of N1 and the second material is nothing but the cladding material. So the refractive index of cladding is denoted by the symbol that is N2. So from core to cladding, your refractive index is changes abruptly. That means from core to cladding, it gives us a discontinuous refractive index. That means if your core has a refractive index of 5 and let's assume that your cladding has a refractive index of 4. That means in step index fiber, you are going from 5 to 4 directly. That means it does not contain the value of 4.9, 4.8, 4.7, etc. So that's why it is known as step index fiber. So in step index fiber, we can see the discontinuity of index profile at a core cladding interface. Now, in the step index optical fiber, the diameter of the core is 50 mm to 200 micrometer for the multi-mode fibers and the cladding thickness is 20 to 25 micrometer. And for single mode fibers, the core diameter is 2 micrometer to 10 micrometer and the thickness of the cladding is 25 micrometer to 30 micrometer. So the step index fibers are cheaper and which is used in short distance communication. Now the second part is graded index fiber. So this graded index fiber, it is also known as GRIN fiber. So this is the shortcut used for graded index fiber. So as we see previous, in step index fiber, the refractive index of core to cladding changes within a step. Whereas in graded index fiber, if N1 is your refractive index of core and N2 is a refractive index of cladding, from core to cladding, you will get intermediate values. That means you will get the value of 4.9, 4.8, 4.7 and 4.6. That means the refractive index is maximum at your core. That means here in this point, the refractive index of core is maximum and from this point, your refractive index is decreases gradually up to the cladding. So gradually decreasing curve is obtained in graded index fiber. In graded index fiber, the core diameter is about 20 micrometer to 100 micrometer and it has a cladding thickness of 25 micrometer. So this type of fibers are commonly used in medium distance communication system. So this is the types of optical fiber. Now let us discuss the difference between step index fiber and graded index fiber. So this point is very IMP for your exams. So let us discuss. In step index fiber, as we discussed earlier, there is a discontinuity in a index profile. That means from core to cladding, you will get a fixed value of refractive index. And in graded index fiber, the refractive index of core decreases gradually to attain the refractive index of cladding. Now the second point is, in step index fiber, the refractive index of core is constant, and in graded index fiber, the refractive index of core decreases within a parabolic manner. Now the next point in step index, that is, the step index has the high attenuation. So what is the attenuation? It is any reduction in the strength of signal, that is known as attenuation. So this point we will discuss later on. Now in graded index fiber, it has the low attenuation. That means attenuation is nothing but the loss of optical signal. Now the next point is, for step index, the diameter of the numerical aperture is greater, and for a given diameter in graded index, the numerical aperture is less as compared to the step index. Now the step index has a cheap and the graded index is costly. So let us discuss the derivation for acceptance angle and the numerical aperture. So here it is in diagram. You can see that the light is incident within an angle of theta I. So here in this diagram, your light ray is entering into your optical fiber within an angle of theta I, and the light will be transferred from rarer to denser. Here in this diagram, the refractive index of core is mu1 and the refractive index of cladding is mu2. So when the light ray is entering in the fiber with the axis of fiber at an angle of theta I, the light ray is initially in rarer medium, and after that it will enter into the core, so that the refraction will be occur, and this angle of refraction will be theta r, and the light ray will become to core cladding boundary. So we will considering this small triangle, that is A, B, C. So in this triangle, we can see that theta r is nothing but your angle of refraction. Phi is nothing but the angle for which your TIR, that means total internal reflection, will be occur. And mu1 is nothing but the refractive index of core, and mu2 is nothing but the refractive index of cladding. So let's start the derivation. So by using Snell's law, we can write that sine of theta I upon sine of theta r, which is equals to mu1 upon 1. So here it is, generally we can write mu2 upon mu1. But here our second media is nothing but the core media, and the refractive index of second media, that is denoted by the letter mu1. So here we have write that is mu1, and for cladding refractive index you have used that is 1. So this is the refractive index of first media, that is your air media. So as we can see that in triangle ABC, the sine of this angle, refraction angle, sine of theta r, which is nothing but the sine of 90 minus phi. So this angle is 90 degree, and this angle is your phi angle. So 90 minus phi, you will get a theta r, and the sine of 90 minus phi is nothing but the cos phi. Therefore your equation is sine of theta r, which is equals to cos phi. So by using equation 1 and 2, we can write that. So rearranging this equation 1, we can write that sine of theta I, which is equals to mu1 sine of theta r. So replacing the value of sine of theta r by equation 2, we can write as mu1 equals to cos phi. Now theta I is replaced by theta max and phi is replaced by phi c in above equation. So this equation can be written as sine of theta I max, which is equals to mu1, and the phi is replaced by phi c. So therefore sine of theta I max, which is equals to mu1 cos of phi c, that is equation number 3. Here theta I max is nothing but the acceptance angle. So now, as we know, cos of phi c, which is equals to square root of 1 minus sine square phi c. So here we are using the identity, that is sine square theta plus cos square theta, which is equals to 1. So we can write cos of theta c equals to square root of 1 minus sine square phi c. So sine of theta I max equals to mu1 cos of phi c. So this is our equation number 3 as we derived this earlier. So we can replace the value of cos of theta pi c in this equation number 3. So we can write this equation as sine of theta I max equals to mu1 square root of 1 minus sine square phi c. So as we know, the sine of phi c, which is equals to mu2 upon mu1. So this derivation we have already derived when we started the optical fiber session number 1. If you don't know this, you can use the video of session number 1 for the optical fiber. Now, so sine of phi c, which is equals to mu2 upon mu1. So we are using this value of sine of phi c in this above equation. So this equation can be written as sine of theta max equals to mu1 as it is square root of 1 minus. So here we replace the value of sine of phi c equals to mu2 upon mu1 square. So by rearranging this equation, we will get mu1 square root of mu1 square minus mu2 square divided by mu1 square. So after taking this mu1 square outside of square root, we will get a mu1, and this mu1 cancels with this mu1. So you will remaining with square root of mu1 square minus mu2 square. So theta I max equals to sine inverse of square root of mu1 square minus mu2 square. So this is the final derivation for the acceptance angle. Here theta I max is nothing but the acceptance angle. So here it is the definition of acceptance angle. So the acceptance angle is the maximum value of angle between the axis of fiber and the light ray entering into the fiber for which the TIR occurs. So what is this TIR? Total internal reflection. That means here it has the maximum value of angle for which your total internal reflection will be occur. So this is known as acceptance angle. Now the next is numerical aperture. So this numerical aperture can be derived by using the derivation of acceptance angle. So the numerical aperture is defined as the sine of acceptance angle. That means NA equals to sine of theta I max, and as we get the value of sine of theta I max equals to square root of mu1 square minus mu2 square. So this is your equation number 5. In this equation number 5, we have to replace the value of mu1 square minus mu2 square by using the formula a square minus b square. As we know, a square minus b square is nothing but the a plus b and a minus b. So after replacing a and b by mu1 and mu2, we can write as mu1 square minus mu2 square equals to mu1 plus mu2 and mu1 minus mu2. So this is your equation number 6. Multiply and divide the equation 6 by 2 mu1. We can write above equation as mu1 square minus mu2 square, which is equals to mu1 plus mu2 divided by 2 and mu1 minus mu2 divided by mu1 and multiply by 2 mu1. So replace this value mu1 plus mu2 divided by 2 by mu1 and the second part, that is mu1 minus mu2 divided by mu1 by del. So by replacing these values, you can write mu1 square minus mu2 square, which is equals to 2 mu1. So this 2 mu1 as it is, this value is replaced by mu1, and already you have 1 mu1 in this equation. So we can write mu1 square minus mu2 square equals to 2 mu1 square del. So after putting the values of mu1 square minus mu2 square in equation number 5, we can write as numerical apertures equals to square root of 2 mu1 square del. So after taking this mu1 square outside of square root, you will remaining with Na equals to mu1 del square root of 2 del. So this is another formula for the numerical aperture. So this is all about today's session. Thank you. Please like, share and subscribe the video.